What are we doing? Something. Yeah, we're good. We hold 18, so.
It all worked out.
Yeah, it's fine. Good. Everyone good online? We had. Okay, how's everyone?
Great.
That's fantastic. Good weekend?
Yeah.
Yeah, very, very short. Stupid. Stupid short. All right. Exercise physiology. Chapter 4. Chapter 4. Sure, everything's good. So, we started off this chapter. I guess we only went through a few slides so far, so continue on. Remember this picture, some of the stuff that maybe an exercise physiologist may or may not do. Sticking things up people's butts, you know, whatever it may be. But checking the physiology of the body during physical activity or even during rest. It doesn't have to be physical activity. A lot of different things you can check. In this picture, you got skin temperature, core temperature, heart rate, and blood pressure were taken. The air coming in and out of the body was also taken. I believe there were some blood draws during this as well. I can't remember what they were measuring there, but I'm sure there was probably also finger sticks, blood lactate, blood glucose. I think that's probably about it. But, well, I think there were some psychological tests also with it, before and after. Some of them were, they weren't like psychological tests that make you crazy type ones. If you've ever taken some of those where you're just like, what am I reading? It's one of those ones where it'll have the word of a color, but you have to say the color of the font or the opposite of that. So if you had the word blue, but it was written in red ink, you had to say red. So and you had to get down a list of 20 or 30 of them. And just see how well you do. And there's other questionnaires and stuff you can do with that. Then VO2 max, maximum amount of oxygen. Body's able to utilize. And another thing too I want to point out is if you just say, oh boy, did it. VO2, that could be at any intensity. It could be at rest. It could be at maximal exercise. I don't know if we got enough room. And just sit on the, yeah.
I'm here the wrong day, that's why.
Okay. You'll be good. It's recording. I think. I hope. So it can be at any intensity, and that would be what's known as submaximal. Oh boy. Oh boy. Oh, that's a crappy looking. What do you raise it? submaximal, below max, anything below max. And then we had the videos. The first one was a VO2 test. There was a couple mistakes in there. Well, major mistake was it went way too long. Probably at least 7 or 8 minutes too long. It was probably really the only mistake that they made, at least that I've seen for that. And then the second one was a Wingate test, also known as a pedal and puke, just a sprint on a bike. That one, the mistake in there was the subject lifted themselves off the seat. They should be seated the entire time. Anytime you're trying to exercise at a certain intensity on a bike, your butt should be touching the seat. With a treadmill, you shouldn't be touching the handrails. Same thing with a stair stepper, because that negates the incline or the decline that you may have. I don't think there's anything else there. So the first one was aerobic, and the second one was looking at anaerobic exercise. So a couple different tests that we could use. Touched on what is exercise physiology. So study the functional and physiological responses, adaptations. We'll go over some responses and adaptations today. Those that occur during and following activity, exercise, and acute and chronic bouts of activity and exercise. I believe we left off here, made the slide a little bit more neat and clean. Development of exercise physiology, a lot of it happened in, some of the major breakthroughs happened in the Harvard Fatigue Lab. Physiological, psychological, sociological responses, they looked at environmental responses, nutritional responses, and that was one picture within the Harvard Fatigue Lab. I don't know if the book says when that picture was taken. I don't know. I can't remember. But you can look the lab up online. I'm sure there's lots and lots of pictures of it. Okay. All caught up. I mentioned it yesterday to a class. When I go through the quick review at the beginning of class, I keep forgetting to put a picture of Deadpool on the new slide and be like, all caught up. But all right, so acute responses. These are changes to the system, to the whole body, and the organs during one bout of exercise. And we've already seen this term once, but response to increased changes to homeostasis. So something has changed that is not, I guess, normal at rest. So there's a change, and the body is going to respond to that. The organs will respond to that. Basically, during any increase in physical activity above rest, there is going to be an increased demand for energy. So we need to get energy somehow, and all the systems are going to start to increase, or most of them will start to increase. The digestive system may decrease a little bit, actually. That's a good thing. It's a good thing. We'll go through some of the changes, acute changes that happen immediately. And here's some lists. Yay. All right, cardiovascular. Right off the top. You may notice as you begin to move around, heart rate starts to increase. pretty sure we went over the calculations of this, the heart rate. Heart rate times stroke volume equals Q. Right? Did we? Yeah, that's right, yeah. Just want to make sure. So we're talking about it in a few different classes, and sometimes you're teaching 6 classes, it's a little confusing. Trying to keep it straight. So heart rate times stroke volume. So the heart rate will increase as we begin to move around. Stroke volume will increase, and there's going to be a little bit of an increase in cardiac output. Blood pressure will also increase. The blood pressure's a little funny, however. I'll try to write it. So let's say, no, maybe not. It's like disappearing on me. Oh, I don't know what. Yeah. There we go. Say you had a blood pressure of 120 over 80. Sometimes referred to as a normal blood pressure, but actually that's referred to as pre-hypertension. But it's still okay. It's not like you're going to have heart disease with 120 over 80, at least immediately. What do these numbers mean? Anyone know? Anyone know what the top number means?
Systolic over diastolic.
Yep, systolic over diastolic.
Systolic.
Systolic over diastolic. What that means is the systolic is the pressure when the heart is contracting. The diastolic is when the heart is relaxed. The top number is always going to be higher. Well, it should be higher. That one's going to change pretty significantly during any increase in physical activity. The bottom number, diastolic, may actually decrease depending upon the person. It's not going to decrease to like 50, but it may decrease to like 78 or 76. If it increases, it's probably, with a healthy individual, it's probably going to be 84, maybe 86, but it's not. It should not go above 100. If it goes above 100, that's bad. It should not increase that much. But the systolic may increase to 170, 180. And that's normal for exercise, depending upon the intensity too, and the activity. If somebody is not breathing during a weight training exercise, such as a deadlift or a squat, their systolic blood pressure may increase to 350, 360, possibly even higher. So putting a lot of pressure in the thoracic region, basically within the rib cage. Yeah.
You said systolic is heart contraction.
Yes.
What is diastolic again?
The heart relaxation. So yeah. When the heart relaxes, and these are the average pressures throughout the entire cardiovascular system over over that whole area within the body when the heart is contracted and when the heart is relaxed. So even though we say that blood pressure should increase, the top one is the one that should definitely increase. The bottom one, it'll increase maybe, but it shouldn't increase significantly. Now, there's also a way to actually take these two numbers. There's a calculation to put them together and make just one number, and that number will increase. But we're not going to go into that. Also, we have a redirection of blood flow. What I was saying a few minutes ago about the decrease in digestion, we only have so much blood in the body. And when we start moving around, the muscles need that blood, more so than the gut and the small intestines, and all the digestive organs. So we redirect blood away from the gut and take it to the muscles. Not all of it. We can't just take away all the blood from the gut, because then the tissues could die. But we take away enough to feed the muscles or the tissues that need it. Pulmonary system, we just breathe heavier. More air in, more air out. The muscular system, that one maybe should be a little obvious too. We're increasing force production, we're moving the muscles, we're also producing a little bit more waste products. Carbon dioxide, heat is also being produced. That's what warms the body up. A lot of the energy that is given off when we start moving around is given off as heat. That's also why we sweat. And then the endocrine system, we have some hormones that are released. And the two big ones, epinephrine and norepinephrine. Anyone know what the lay terminology for those are called? Epinephrine is probably the most famous one. Adrenaline. Oh, it's kind of working. Adrenaline. And then norepinephrine is known as noradrenaline. Ah, very unique, very unique. So these will do a lot of things. They'll help to increase blood pressure, heart rate, stroke volume, breathing rate. And adrenaline gets a lot of the glory, but noradrenaline is pretty powerful too. It can actually maybe last a little bit longer. It takes maybe a little longer to take off and increase in concentration, but it's basically as powerful as adrenaline is. Questions? So some basic responses during physical activity. Chronic adaptations. These are changes to the system, the body as a whole, to the organs, tissues, during repeated, regular physical activity. It needs to be regular. So if it's just once a week, probably not going to have much of an adaptation. Maybe a slight adaptation, but not much. And if you start skipping weeks, then you're going to start to lose a lot of those adaptations. The major reason is because to keep certain tissues, or to keep any tissue, really, that is adapted for aerobic exercise or strength purposes, it takes a lot of energy to keep it. And if we're not using it, the body is just going to get rid of it. Now, one of the cool features about this is that not only do we improve some of these parameters, heart rate, blood pressure, stroke volume even, during exercise at submaximal and maximal, but we also improve them at rest. That's why a lot of long distance runners have a very low heart rate at rest. On average, resting heart rate is, I think the actual average, the entire population, somewhere around 75, 80-ish. If you probably take the average heart rate, resting heart rate, marathon runners, it's probably 40s, maybe low 50s. So it's significantly lower. So the heart rate improves. And some of the chronic adaptations. So with the cardiovascular system, stroke volume is increased. That's actually causing the decrease, or part of the reason why there's that decrease in the heart rate. Let me go back to this. Stroke volume times heart rate, or heart rate times stroke volume equals Q. Let's say if we look at somebody who went through, let's say, 2 months of aerobic exercise training. You know, we looked at stroke volume, heart rate, and cardiac output before and after. At, let's say, 50% of their VO2. So halfway to maximal exercise. At that intensity, the same amount of blood, about the same amount of blood volume is necessary to feed the muscles and feed the tissues that need it. So that's the same. Cardiac output's the same. But the heart is actually a little stronger. And there's even some hormonal adaptations here that can cause the stroke volume to increase. The heart can expand a little bit more, and when it expands just a little bit more, it can squeeze out more blood. And when it squeezes out more blood, that is stroke volume. And because we've kept cardiac output the same, the heart rate's going to be counteracted by decreasing the amount of beats per minute. So we're keeping the same blood volume per minute, it's just we're changing the stroke volume or the heart rate just a little bit. So that's the major adaptation there, and that's why the heart rate will go down. Pulmonary system, air in and out of the lungs. There's also an increased blood flow to the lungs to help with getting oxygen, but also getting rid of carbon dioxide. In terms of increasing volume in the lungs, there may be a small increase, but it's probably not a lot. The actual capacity of the lungs is likely somewhat set once you reach full adulthood. However, there is some anomalies in this. World-class swimmers, like elite swimmers, tend to have higher lung volumes than the average population. It's probably a chicken or the egg question. Which one came first? Are they elite swimmers, partly because they have higher lung volumes, or do they have higher lung volumes because they train so much with their lungs? Right? There's a lot of lung and respiratory training with the type of swimming they're doing. It's likely that they just so happen to have high lung volumes, which makes them that much better swimmers than everybody else. So, there's other things too that go along with that. It's just not the lung volume. The muscular system, there's an increased energy production going actually to fat. the more trained we are, the more fat we actually burn at lower intensities, below maximal exercise. Now, once we get to maximal exercise, it's always going to be carbohydrates, doesn't matter. That lactic acid that is formed, not only is it not formed at lower intensities now in large amounts, like maybe it was before training, but we're able to clear it out faster also. There's an adaptation to take it back. You actually take it back to the liver, and it goes through a process to make it back into glucose and back into sugar. It's reusable. Cool. And then the endocrine system. There's actually a decrease in epinephrine and norepinephrine. We don't need as much of it for the same response as somebody is trained. Now, most of these are specific to aerobic training. Some of these you'll also see in anaerobic training as well. Even a little bit in strength training. But mostly the aerobic training is what we're talking about here. What's that? Just the same workload that you were working at before. Set at 50%, the best graph with this example. So 50% is the absolute workload for that. You could also, there's a couple different ways to describe workload. It could be a percentage of VO2. It could be watts. You could maybe even say like kilocalories per minute or hour. There's also another one called METs. I don't think we'll get into. A lot of exercise equipment at gyms, you can set it to watts. You can set it to METs. Or kilogram meters per second squared if you wanted to do that as well. That's any other questions on that? Adaptations? Nothing online from the chat? All right, so stuff that's controlling metabolism, substrates. And when we say substrate, we are meaning the material that we're getting energy from. So that can be fat, carbohydrates, could be protein, could also be alcohol. So it's the interaction between them and when they are being utilized more. Intensity and duration being the biggest factors here. And also if they're available. If you have no more carbohydrates to use, then you're not going to be using any carbohydrates. Enzymes and hormones in their availability. Was it last chapter we touched on this about the carbohydrates and the fats? We got a crisscross there with the intensity. Yeah, so we got basically the same graph. Great. Right, y'all. So as we get closer and closer to maximal exercise, we're going to be utilizing more carbohydrates or ATP or energy. Now, lower and lower intensities, we're going to be burning more fats. Now, the longer the duration, likely the lower the intensity, so therefore we're going to be burning more fats. Speaking of carbohydrates and sugar, control of glucose uptake, or the body's sugar source. So regulation, energy utilization during physical activity, exercise. The main goal here is to get glucose into the cell. If you can't get in the cell cannot use it. It can't go through the metabolic processes that it needs to. Be broken down, we get ATP, we get energy from that. Now we don't convert the energy, we just transfer it from one form to another. And if we could convert energy, oh man, that'd be pretty sweet. Our bodies, like, this would be our metabolic equation. We could convert energy. That'd be pretty awesome. That's right. Yeah. So that Snickers bar would end up becoming, I don't know, probably enough to blow a hole in the vicinity and blow a hole in the earth. But thank goodness we don't do that. We just transfer it from one form to another by breaking bonds and then putting new stuff or putting molecules in other places. So we don't do that. Now there are certain receptors that are going to be necessary for the glucose to get into the cell. And insulin is going to help to get glucose into the cell, but there needs to be a receptor on the cell membrane for this to work. And it also needs to be functioning properly. If there was a disconnect there with the insulin and its receptor, then we're going to have a problem. The glucose cannot get in the cell, and blood sugar is going to continue to rise. That's where we have diabetes. That's type 2 diabetes, specifically. Yep, sorry. Type 2 diabetes. Type 2, there's a problem with the receptor. We can produce insulin, we can produce insulin, but for some reason, something is happening where there's a miscommunication between the cell receptors and insulin. Type 1 diabetes, the individual cannot produce enough insulin, so they need to have injections of insulin in that case. Skeletal muscle physiology. The muscle fibers themselves go under some differences in metabolic characteristics. Whatever type of training it is, they're going to adapt to that, mostly. When we go over the different fiber types, type 1, type 2A, type 2B, or type 2X, they naturally have some certain characteristics. Type 1 being, what, aerobic, anaerobic, remember? Type 1 muscle fibers. Yeah, aerobic. Type 1 muscle fibers being mostly aerobic, so using oxygen in large amounts. Then the type 2 are mostly anaerobic. But if you're training for aerobic training, the type 1s are going to still do their thing. They're going to have a little bit more adaptation. But the type 2s are also going to start to shift a little bit more to oxygen utilization. Mostly the type 2A. The type 2B, those ones may have some adaptation, but they're still mostly going to be used for strength purposes and maximal force production. The type 2A are going to start to look a little bit more like the type 1. Not completely, they're not going to shift over and change, but they'll look a little bit more. They'll adapt to it. On the reverse, if you're training more for strength purposes, a lot of power, explosive events, the type 1s may gain a little bit more strength capabilities. They'll lose some of the adaptations for aerobic. And then the type 2s will also do the same thing. They'll lose some of the aerobic adaptations that they may have had and gain a little bit more strength capabilities. There is a possibility to change fiber types. It takes a while. If it does happen, we're talking many months, if not a few years of continuous type of training. The major research where that has been found is potentially sprint training. And people went for, I think it was anywhere from 9 months to 15 months of 200-meter dash type of sprint training. Then they showed that there was a potential to change fiber types. But it's still variable. We're not 100% sure because it's tough to figure it out, because the only way to figure it out is you need a sample of the same area of muscle fiber or muscle fibers, and that's with a muscle biopsy. And so it's basically a core sample of the muscle, and to get it in the same exact spot, same exact muscle fibers, months apart, it may be a little difficult. So, but we think it does happen. That's actually fairly new research too. We didn't think that that was actually possible in humans, but we do now. All right, certain areas of study, kind of subfields, exercise physiology. Strength development, strength conditioning type stuff. We have looking at the exercise intensity, how that is going to affect strength development, the frequency of it, and then how does maybe only training, weight training each body part maybe once a week, twice a week, maybe every other day, 3 times a week. What about every day? Duration of the exercise training, how that's going to affect strength development. And then if you start combining some of these, exercise intensity, the frequency, and then also the duration of each training session, how's that affecting it? Types of exercises that are selected, maybe what's best for certain activities, for certain sports, performance increases, maybe even certain decreases in risk for injury. Total amount of work that is performed. A lot of times with the total amount of work, it's just taking the sets times the reps times the weight. That would be the total amount in terms of the strength development from a weight training point of view. How does age and gender play a role? Plays a major role, especially once we get past 25 or 30. Our metabolism starts to decrease, our strength capabilities start to decrease, maximal strength capabilities start to decrease. It's all over from there. So, pack it in. No, it's totally fine. Most days. Most days, it's fine. And then the fitness level. The starting fitness level is going to affect how much of an increase somebody can have. If they're starting off really low, even if they're 40 years old and they've never weight trained a day in their life, they're going to have a much larger strength capability increase than somebody who has been training for 20 years who is 35, a little bit younger. All things being equal, they should have about the same capabilities. Some of that is based upon genetics. That's going to be the major factor in any type of training capabilities, actually. Bone metabolism. The bones are similar to the muscles in that they will respond very well to exercise training. In fact, they need some stress on them. They need weight and force being applied to them to be strengthened. And I think I mentioned that's why astronauts need to be able to do some type of weight-bearing exercise in space, especially if they're there for months at a time. So something to put stress on the bones to keep them, keep most of their mass. Some of it still may deteriorate because they're still not exposed to gravity and just their body weight on a daily basis. So they need to have some form of either simulated gravity, some type of centrifugal force, or weight training, strapping themselves in and doing some weight training in space. If that doesn't happen, if somebody does not have enough weight-bearing exercise throughout the day, they could develop osteoporosis. Some of it is also hormonally related and nutritionally related. Excuse me. Big one being not getting enough calcium in the diet. There's other minerals too, magnesium, phosphorus. And osteoporosis is just an increased risk for fractures because of decrease in bone density. There's a specific number that you can actually use. There's a certain test, but the actual general definition is just an increased risk for fractures because of decreased bone density. Questions? Any from the online guys, gals? Okay, cool. Osteoporosis. Another area of study. This is a very specific area that's studied quite a bit too. So this is known. Yeah, right. Smart boards aren't very smart. Now I just changed the color font. Okay. Oh, speaking of which, that psychological test. Say the color of the font, and then so that you have a whole bunch of them like that. Yeah, okay, never mind. Side note. All right. Female athlete triad. So those three terms are very specific to what this entails. It's females. They don't necessarily have to be in athletics, but it has something to do with training. And there's three components to this. That's why it's a triad. The first one being low energy availability. Most often this is associated with an eating disorder, either anorexia nervosa, bulimia nervosa, so low amounts of energy and nutrients. Along with that, there's probably an over-exercise. Most often there's an over-exercise. Too much exercise, really. So not only are they not getting enough nutrients and calories, but they're also exercising 4, 5, 6, 7, 8 hours a day. So body image disorders, and this is messing up some of the hormones as well, not just the nutrients that could possibly cause the other portion of the osteoporosis, but that also reduces the hormonal responses to help to build the bones, and also could cause amenorrhea, or basically a major disruption in the menstrual cycle. That also causes a major disruption in hormones, which then also adds to the osteoporosis. So all three of these are interrelated. Luckily, there's treatment for it, and hopefully getting back to optimal energy intake, nutrient intake overall, and the bone health improving, and the menstrual cycle getting back to normal cycles. Mostly seen in teenage females, because the major component here, and what usually starts it off, is there's some body image disorder, and then there's an eating disorder then that will follow it. And sometimes they'll go back and forth between bulimia and anorexia. Any questions on that? So very specific area to study, but it is studied quite often in the field. Speaking of energy balance, intake, energy balance and weight control. So promoting overall good health. Kind of that Goldilocks zone. Getting enough food, getting enough calories, but not too much, not too little. Just right. Sometimes that can be problematic and it can be difficult. Trust me, I know. So the goal here is optimizing performance for any athletes. Also trying to decrease the risk for any disorders, diseases that may occur, injuries, and also maybe even optimal nutrition for recovery from injury. There are multiple energy balance equations that can be used to determine approximately how many calories somebody needs. There are different charts, how many carbohydrates, fats, proteins, calcium, magnesium, vitamins, minerals. There's a lot of different charts and tables that can be used. Luckily now, it's fairly easy, much simpler than it was even 15 or 20 years ago, because everything's online, can be computerized. You can type in almost any food and you can get the nutrient content, or at least it'll be close. It may not be exact, but it'll be the close nutrient content of that particular food. And a lot of that is free now. And some of the analyses is free. You can type in what your meal was, and you basically got a total breakdown of the calories and all the nutrients. Back when I was an undergrad, you had to pay for that, and our nutrition book was, the CD came with it, and you got the program for free. It didn't have very many foods. It had most foods, but if you wanted the full program for yourself, I think you had to pay like $2,500 or something like that. So it was crazy. Now everything's on your phone. That was also a time too when PDAs were also popular. So they basically kind of looks like your phone now. Well, they kind of look like your phone, but they were almost like Blackberries. But they ran like Windows on it, and they had a whopping like 50 kilobytes of memory. Oh man. And they sold for like $800, $1,000. Yeah, it's fantastic. People walking around with, often they had styluses with them. Oh yeah, yeah. It was awesome. Whew. At some point, I'll show you a nice video of the Apple Lisa computer commercial from the '80s. Anyway, continue on. All right. So that energy intake, some factors that can affect it, some things to study. The living and work environments, and some of that can be who's around you. What are some of the peer influences that are maybe positive or negative in terms of the energy intake? Genetic profile, this one is the biggest one. Genetics plays a big role in almost anything. Energy intake, expenditure, a lot of times, performance. In fact, there was, I don't know if I've said it in this class, I say it all the time. I used to have the quote on my door. I don't even know why I took it off, but I need to put it back up. A guy by the name of Astrand said, if you want to become a world-class athlete, you need to choose your parents wisely. So that's good piece of advice. Maybe, I don't know. Socioeconomical status. Sometimes good food, good nutritious food can cost a little bit of money. And it may not be available in some areas. Psychological state, that one can go both ways. If you're stressed, some people overeat when they're stressed. Some people don't eat at all when they're stressed. They don't even drink any water or anything. So that can kind of go both ways. Also, when you're stressed, the hormone levels get out of whack as well. And that can affect metabolism. Resting metabolism. The exercise patterns that somebody has, the more often they exercise, or on a regular basis, the more regular it is, they tend to have a better metabolism, a higher metabolism, more. They'll be burning more fats throughout the day. Usually, their psychological state is better as well. Usually, not always, but usually. And then availability and selection of macronutrient content, that kind of goes into some of the socioeconomical stuff, where in some areas maybe some nutrients, some foods are not available. It may cost too much. You just don't want to pay for it. Some of the best foods, especially for somebody who's a vegan or some version of vegetarian, is nuts, cashews, as long as you're not allergic to peanuts. But sometimes they can be expensive. You get a nice can of roasted peanuts or something like that, or like a whole can of cashews or walnuts. Man, those things are expensive, like 15 or 20 bucks for like a small can. So, and you can eat that thing in one setting, so it doesn't take long. Even some lean meats. Meat especially now, because there was a shortage, and, you know, it can be expensive. Questions? All right, we'll finish this up on Friday, I think. One of these days, I don't know if it'll be Friday, possibly Monday, we'll have an activity. I'll look at the weather, see what everything's going to be doing, and one of these days we're going to go outside, you know, and do something. So it'll be fun. Maybe, depending upon what you consider fun. Yeah. Thank you, guys. And